next class that starts today.
Oh, yeah, well, is it summer class as well?
Yeah, mechatronics.
All right. Well, welcome everybody. Thanks for making it out to the class. Today we are going to be covering session 20, absolute maximum shear stress. But before we get to it, I'd just like to point out where we are on the schedule. So if we look at where we are, we're right here, session 20, absolute maximum shear stress. Today is the 26th of June, and tomorrow we're going to cover plane strain, okay? And we're going to look at more circle and plane strain. The exam number 2 is on Wednesday, and that will cover material up to session 20, okay? And so today's assignment that will be assigned, or that's repetitive, that we have, that will be due tomorrow. The one that's session 21, that will be due on Thursday after the exam. Okay, does that make sense? So hopefully, there's enough time, and you've already been spending time looking at a lot of the material on in-plane stresses, on more circle, and so what we're adding today is significant, but if we've got a good handle on what we've covered up to this point, it's not going to be too painful. Just looking at where we are in the course, it's kind of exciting because we're almost done. We really are. I mean, there's quite a bit of material still to cover, but we have, after today, we have 1, 2, 3, 4, maybe 5 sessions, okay? And then we have a little bit of a buffer on the 5th of July, and we'll be able to then have the final exam on the 6th. Any question, about, any questions about what we're doing in terms of where we are on the course, pace, the content? Okay. All right. Well, that's good. And of course, if you want to get ahead, you can, all the material this semester, fortunately, is pretty much up there. There's some minor tweaks and updates, but it's there for you. And also, the in-person live sessions, those are up on the website as well. If you want to take a look and review what we've kind of covered, or if you ask the question and you want to go back and hear the response, that's up to you. That's available to you. All right, so session 20, absolute maximum shear stress, okay? And also, before we even get there, a little bit about principal stresses in 3 dimensions, okay? So this session, the main focus is on absolute maximum shear stress through Moore's circle, okay? That does not come up though until part 2, okay? That's really part 2, but that's the main focus, and definitely relevant to exam number 2, okay? So this is very relevant. But before we get there, I thought it would be interesting to talk a little bit about another state of stress, which is part 1. Of this session, and that's called triaxial stress. And the basic idea is that you can have some 3D element some 3D element, and I can put some stresses on it. Oops. Something like that. And maybe the state of stress looks something like this in terms of a tensor. Okay, so this is like a general state of stress in 3D. Okay, which is not something that we typically focus on studying in this class. But if we have this general state of stress, we can rotate or change orientation such that we find only principal stresses in all three new dimensions, okay? In the new, what are we, x prime, y prime, z prime, essentially. And we have sigma 1, sigma 2, sigma 3, okay? So that all these other terms, those would be zeros. Okay, so there's no shear stress.
Is that just reduce area? Like, can you do that?
Say that again, Michael?
Can you just do the matrix transformations and put in reduced REF to find out?
Yeah, so you can, yes. So this can be solved a couple of different ways, all right? One is, yes, to use linear algebra and to solve an eigenvalue problem, okay? And the eigenvalues, so this is beyond the scope of what I really expect for this class, all right? But the eigenvalues become, and I mean, I do cover it, and and it's implemented. You have the code in Colab to do the eigenvalue problem, but the eigenvalues become the magnitudes for sigma 1, sigma 2, sigma 3. And then the eigenvectors become the directions, the unit vector directions for sigma 1, sigma 2, and sigma 3. And those eigenvectors are going to be orthogonal. So they're going to define another coordinate system, okay? So it's pretty neat that we can get, essentially, you rotate. So you rotate, and there are different ways you could do the rotation. There's a technique where you find interesting axis, okay, and then you do only one rotation to get to the new state. Or you can do 2 rotations about other axes to get to the final state, all right? Again, not going to be on exam number 2, okay? But this is for your kind of good to know file, right? We've already seen in the class that in 2D, right, for in-plane stresses, we can find a state where we have no shear stress. Okay, we've already covered this, and this is just expanding it to the next level. So if you look at the notes, so yeah, all right, well, I'll just finish my thought here. So if we rotate and we get to a new state of stress, oops, what did I do? So we rotate and we get to some arbitrary new state with a really bad looking cube, and the vectors coming out of this thing are only normal stresses, okay? Only normal stresses. And again, you ask yourself, why do I care? Why do I care about this? And the reason that we care is some materials, like the brittle ones, they fail because of normal stresses. That is their dominant mode of failure due to normal stresses. So if we have some arbitrary state of stress with shear stresses and normal stresses, we can rotate the element to get to a state of normal stress, and we can look at criteria for normal stresses if it's a brittle material and say, okay, we now think it's going to fail because from the criteria, which we will cover later, we will have a normal stress or a combination of normal stresses that exceeds some threshold which we predict will then cause a failure. Yes?
So is there gonna be like, there's two angles, right? That it's rotating?
Yes.
So does that mean there's 4 different combinations of the two angles that can control?
Yeah, you can get there different ways, yes. I've had to think a little more carefully about. So there's a phrase that says finite rotations do not commute. All right, this is from Professor Baruch in our department in his book on applied dynamics. So they're not commutative, right? So you think, right, we have operations like addition, right, multiplication. You know, it doesn't matter which one you do first. In this case, it gets a little bit tricky with the rotation. So if you say, I'm going to do a plus 30 degree rotation about this axis and then a minus 30 degree rotation about this axis, if you say I'm going to do the minus 31 before I do the 30 plus 31, you're not going to get to the same orientation. Okay. Again, beyond the scope. I like the questions. Beyond the scope, right? So in the notes, what you'll see is that we are attempting to go from some generalized depiction of stress, like you see here, or you see here, right? Because the Cauchy stress tensor is given by just sigmas, but we can also write them out as sigmas and taus. Okay, so we go from that state of stress to some orientation of what's called triaxial stress. So this is state of triaxial stress when you have only normal principal stresses in 3D. Okay? And one method of finding these principal stresses is to set up these invariants, I1, I2, I3, and then solve for the roots of sigma 1, sigma 2, sigma 3, as you see here. And this will give you the sigma 1, sigma 2, sigma 3. All right, so this is a third order polynomial. And so there will be 3 roots that solves this equation with these invariants. If you want to solve it, actually you will like to solve this, all right? I highly suggest that you just use the code that I'm giving you, all right? Now, if we're interested in calculating out the maximum in-plane shear stresses, we can do so using the sigma 1, sigma 2, sigma 3. So first, what you would have to do is you figure out what sigma 1, sigma 2, and sigma 3 are. That's, in other words, we're figuring out what are the principal stresses in 3D. And similar to what we've done previously, we can use more circle, okay, or use our understanding and figure out then what the maximum in-plane shear stresses would be. Let's say on the in the 1-3 plane, in the 2-1 plane, and the 3-2 plane. Okay. Again, this is a little bit beyond what you would be expected to do for exam 2, mostly because it's pretty, well, compared to what we've been doing, this is a little bit more computationally intensive, okay, numerically intensive. Now, here's an example. You can go through it. Again, I highly suggest that you use the collab that you've been given. In this case, it's back here. Okay. to be able to calculate out the appropriate values. Again, all you've got to do is hit Control Enter at the beginning, and then run it, and it will tell you the principal stresses. Okay, that's all you got to do. And you can change, right? You can put in different. So this is saying, given some initial state of stress, sigma x, sigma y, sigma z, tau xy, tau xz, tau yz, right? So the 6 defining values for the stress in 3D, and it spits out the principal stresses. Now, another way to do this is to use the eigenvalue solver, okay, which is in here. So, well, actually, this is using eigenvalue, right, solver, and then this is using the roots, okay, technique. Here's what you see: roots, and you see eigenvalues, right? Either way, it will solve the problem for you. Now, so this is not going to be on exam 1, but it's, I think, interesting intellectually to be able to understand what we can get if we orient the element differently in 3D. What will definitely be on exam 2 is this section, all right, on absolute maximum shear stress. So we just discussed, and in fact, we said, oh, hey, if you figure out, like, if you want to take your calculator and you want to have it spit out sigma 1, sigma 2, sigma 3, and then you want to use these in maximum in-plane shear stress formulas, you could do that, all right? What we're going to show, though, is a graphical method, right? This is not really a graphical method. Where is it? Right, this is not really a graphical method. This is a mathematical method that spits out an answer. Absolute maximum shear stresses can be calculated without too much difficulty for our kind of 2.5D problems that we've been doing up to this point. And why do we want to know what the absolute maximum shear stress is? Any ideas? Like, based on what we just said about why we want to know, maximum normal stresses, why would we want to know absolute maximum shear stress?
To see like where the material will fail.
Right. And what kind of what kind of material are we talking about?
The brittle.
So not brittle, but the ductile materials, right? And again, it's a little bit unfair because we haven't really gone through failure criteria yet, okay? But your steels, your aluminums, okay? These ductile materials, these are the ones that fail because of shear. And so we were kind of saying before, oh, I can figure out what the maximum in-plane shear stress is. And that could be important to determining why a material fails. But it turns out, even with a 2.5D problem, the largest shear stress may not be in the plane that we've been discussing, okay? And so that means that we would like to figure it out, okay? Because we care about failure, and we will care about failure more in the future. So you can go through the video, okay? There are kind of 2 cases that are important that you want to think about, okay? And those cases are where the absolute, or you have principal stresses, okay, that are both positive. All right, so the video does a better job than I can do right now, okay? But what you'll see here is you start with a state of positive, right? So sigma 1, sigma 2 are in tension. I guess maybe we should back up and say, look, what we've done is we've said, I have found the principal stresses in 2D, in a plane, right? So that means that if I gave you a sigma x, a sigma y, and a tau xy, okay, that's what plane stress is for us. So 3 parameters, sigma x, sigma y, tau xy. You make your Mohr circle, all right? And I highly suggest you be able to do this. I give you sigma x, sigma y, tau xy, you make your Mohr circle, and then you figure out what sigma 1 and sigma 2 are. If sigma 1 and sigma 2 are both positive, in other words, this state where they're both coming out of the element, two tensile stresses, two normal tensile stresses, then let's say that's this Mohr circle right here. All right, and so maybe I will go ahead and do this. Let's do. I mean, I don't think I can outdo myself, but let's point this out. So we start with a sigma x, sigma y, tau xy. Okay. And you know, let's say that on Mohr circle, it looked something, how do I even do it? I should know how to do this, right? Well, let's just say it looks something like this. Okay, and that this was a sigma x, tau xy, and this was the sigma y minus tau xy. Okay, and then we draw our fancy dancy Mohr circle. So if we've got this, then what we do is we say, I want to know where sigma 1 and sigma 2 are. So those are the purple ones. So this is some sigma 1, this is some sigma 2. Okay? Now, if we look at this image over here, let's say that we define the x and the y being aligned with sigma 1, sigma 2. All right? So maybe this is really an x prime and a y prime in our case. All right? But let's just say we've got them defined. Now, if we switch, if we look at a different perspective, okay, what is the perspective we're looking at? We've taken this element, all right, where we had the stress, right? We've taken the element, we have the stress like this, and this is x, this is y, okay? And now what we're saying is we're going to take x and we're going to rotate it like this. So now x, okay, is coming out at us, okay, and y is coming up. And now z is going this direction. And in fact, this is, let me make sure. Okay, no, I flipped the other way in this case. I flipped the other way. So x is going into the board. I flipped it into the page. Okay, so x is going in. All right, not coming out. Look, what happened to sigma 1? It doesn't really matter if I flip x either way. Sigma 1 is no longer in the plane and not in, it's no longer in, it's not in the YZ plane. Okay? It's into the board, but it's not in the YZ plane. So if I were to draw a Mohr circle now for the YZ plane and I ignore what's happening in X, what do I have? I have a sigma 2 over here, and I have what we'll call sigma 3 of 0. Right? Because look, there's nothing in the Z direction. Okay? There's nothing in the Z direction. So if I come back here, there's nothing in the Z direction, and I draw a sigma 3 right here. Okay? Because this is, we're going to say, there's nothing no stress when I say nothing. No normal stress. Because this is a state of principal stresses. Okay? And if I were to draw the Mohr circle, I have a sigma 2 and I have a sigma 3, I can draw another Mohr circle like this. Okay. So that's the Mohr circle there. Now, if I take another orientation, look at this. We can rotate another way where we have now y, so it's like flipping it down so that y is now into the page. Y is into the page, and x is still to the right, okay? And z is now up. What's the Mohr circle for this, for the xz plane? Well, there's only a sigma 1, right? And there's no y, that's going to be 0. So we have sigma 3 again equals 0. So if we come over here, I've got a 0 point and I've got a sigma 1 point. I can draw yet another Mohr circle. Which color should we use? Which color should we use? We'll use red. Like that. Okay. And once we've drawn all 3 of these Mohr circles, we pick the one that gives us the maximum shear stress. Which one gives us the maximum shear stress? George. Which of these circles is going to give us the maximum shear stress? You're looking at me, so Sean, maybe you have it. Yes, it's the biggest one, all right? That's the one that's going to give us the maximum shear stress, right? So the maximum shear stress is going to be dictated, okay, by tau absolute max, right there on the biggest. It's because of the radius, right? This is the radius of that. Okay. So before, if you had just seen, if I had just seen, if we had just had a problem where we said, hey, look, this is the state of sigma 1 and sigma 2 in the xy plane. We would say, what was the maximum in-plane shear stress? You're probably wondering, why is it so complicatedly long to say maximum in-plane shear stress? It's because we had to be very specific that it was just the maximum stress in that plane. But what we're saying is there exists another plane, this xz plane, where we have a larger shear stress, a larger radius of the Mohr circle. And so that's why we need to, this one we can designate as the absolute maximum shear stress. And this one we can say for a particular criterion that a ductile material could fail because of this, okay, by absolute maximum shear stress. Okay, question, yes?
That's always gonna be just, isn't that always gonna make a square from the edge of the circle?
I'm sorry, what do you mean by a square?
Like it's it's from the edge of the, like it's from sigma 3 to the center, which is the radius, and then from the center down to the other edge, which is the
Okay,
radius.
yeah. So we would have a sigma 1,3 average, right? It's just like we've done with other Mohr circles. And so this one is, the middle of this is sigma 1,3 average. And yes, R is going to be from the sigma 1,3 average to sigma 3 to the absolute max to sigma 1. Yeah. Okay, now, there's the other case. So this was the case where, this is the case where both sigma 1 and sigma 2 are greater than 0. There's another case where you get a sigma 1 and a sigma 2 and they're not both greater than 0. Okay? In this case, for example, and sigma 2 is less than 0. So what does this correspond to? This corresponds to a state of stress, all right, that you've gotten to, where let's say that sigma 1 is positive, but sigma 2 is putting it in compression, okay? Right, because normally we'd say out is positive, in is negative, right? So, and this is maybe a little bit confusing. I mean, technically, right, it should be something more like this. And then I say, oh, okay, well, sigma 2 is less than 0. So then we know that's in compression. So when this happens, what we do on Moore's circle, actually maybe I'll do it a little bit more like this. Okay, let's say that we have our sigma 1 and our sigma 2. Okay, it doesn't have to be completely symmetric. Okay. So in this case, if I rotate, let's say I rotate about the 2 axis, okay, and I'm looking at it, what do I see? If I rotate about the 2 axis, and now I have sigma 1 pointing at me, the 1 axis pointing at me, if I look at that plane, all I see is sigma 2 and nothing else. Right? I mean, it's poking me in the eye, so I probably see it, but I'm just visualizing the other plane. So that means that the sigma 3 is again going to be 0. Okay. And if I take this element and I rotate about the 1 axis, okay, 90 degrees, what do I have? I have a sigma 2 poking me in the eye, and all I see is sigma 1. So then again, the sigma 3 is 0. So when I draw the Moore's circles, initially my Moore's circle was this, blue one. But then I actually have 2 more little guys inside. Okay? George, which one of these is going to give us the maximum shear stress? The biggest one. All right, 2 for 2, right? The biggest one is the one that gives us the right? So in this case, all right, when sigma 1 is greater than 0 and sigma 2 is less than 0, what we had as the maximum in-plane shear stress is actually the same as the absolute maximum shear stress, right? So the in-plane, in this case, the in-plane, and this is, we're talking about the 1-2 plane, max shear stress is the same as the absolute maximum shear stress. Okay. So that's the whole thing. So what do you get to do? You get to take what we've done with our Moore circles in the past and add a sigma 3 at the origin, draw 2 more circles, and then figure out which is the biggest. Yes?
Is the right circle supposed to be bigger?
Yes, it is. It is. Because I drew sigma 1 a little bit, I tried to make sigma 1, like this diameter is slightly bigger than the sigma 2, sigma 3.
And how is the radius?
Why is that though?
Yeah.
That's because I picked. That's what I picked. You could have sigma 1 less. So if I could take the absolute value of sigma 2, and if the absolute value of sigma 2 is greater than sigma 1, right? This is just arbitrary.
Oh, so, okay,
I could have easily written it this way. Could have easily written it like this.
Could they be the same if sigma 1 and sigma 2, their magnitudes were just equal?
Yeah, yeah.
So it's
Right, and what would be cool, right? What would be cool about that if they're equal? This is a good point, Owen, right? So this, right? This again, I draw my more circles, right? Little bitty one, right? And the big one is the dominant one, right? But what happens? That's almost worth another page. What happens when sigma 1 is equal to minus sigma 2? In that particular scenario, we'll call this one sigma 1. I'm trying to make it somewhat symmetric. Look, this sigma 3 is again at the middle. I didn't quite do perfect, okay? But we can say that the sigma 1, 3, because we're going to call it sigma 3, or sorry, sigma 1, 2 average is at the origin. Okay, so we'll say this is a sigma is at the origin or equal to sigma 3, right? Or so, you know, we'll say this is the sigma 1, 2 average right in there. What is cool about this? Something very cool. This is in a state of pure shear, right? We have a state of pure shear because when we get to here and here, the tau absolute max okay, there's no normal stresses, right? There's no, at this state, pure shear without normal stresses. Okay, and that's an important case. So we can think of this, if you want, as a rod or a shaft being twisted. Okay, that would be equivalent to that, and we could figure out what the principal stresses are, where sigma 1, okay, is positive and sigma 2 is negative. Right. So in the state of pure shear. Okay, if we said we had a TF, okay, and I took an element here on the surface, okay, so this is a little bit hard to see. Let me draw the TF a little bit differently. Okay, that's pretty. I think that's more clear, right? We're as clear as mud. Okay, so and then I've got that element. So the way I draw these, okay, this is on the top surface. The way I draw this is I say, okay, this is twisting this way. Then I visualize the deformation, and so this is pulling this surface this way. That means that this surface has to be going the opposite direction. Okay, and then that in order for these to be in equilibrium, I've got to draw them like that. Okay. So this shear stress is tau absolute max, okay, in pure shear for this particular case. And what does this mean? That means that if I rotate 45 degrees, remember, 90 degrees rotation on Mohr circle is 45 degrees of a 45 degree rotation on a regular element, right? Because we have a 2 theta. So if I take this, I started with this element. Yeah, let's just do it this way. Okay. And I rotate 45 degrees. That's not quite 45. rotate 45 degrees. My new sigma 1, okay, this is 45-degree rotation, is going to be equal to, well, it's the same thing. Sigma 1 will end up being equal to the tau absolute max, right? But then I have, look, if I go from here to here, right, sigma 1 is positive, okay? But then the corresponding sigma 2, it's negative. Okay, so that will be in compression. Okay, and this is compression. So technically, right, if I drew it the other way, right, I could say it's coming out and sigma 2 is negative, or I could just say sigma 2 is positive here and it's in compression. Okay, or I could say the magnitude, right? So this is a very interesting case that you just pointed out, Owen. And one you should be familiar with. Okay. That's pretty much a long overview of what's in the videos, and hopefully will help as you go about working on the problems. All right, great. So we'll give you some time to think and watch and work.
So how far away is the Bush Student Center from here?
Literally right over there.
I would say quarter mile.
Yeah.
Why? What did you guys say?
It's a mile and a half.
You didn't run track or cross. Did you? Okay.
So I didn't expect that.
Jesus, blew my spot, man.
But I mean, how many meters is it though, right? There's a question that will flex us all. I don't know.
It's a 0.3 mile walk.
All right. Well, hey, 0.25 miles is,
There we go.
we're pretty close. You said quarter mile, right?
Man, I wish
If you wish you put some money on that bet.
I should have put, yeah. I put $1 million on.
All right. Let me just take the attendance. What did you say, George?
You can mark him out as a new list.
Oh.
I don't know.
So he's put $80,000, so he's paying like $5,000. But everyone's like, bro, you literally want something fucking done.
How would I do this?
It was his late mother. Yeah, but he's saying it's long. Dude, I think we're going to keep on class to April 4th. And it's 2 mechatronics. But we need it as a fucking prereq for mechanical measurements.
Oh, is it really?
Yeah, why?
I would take it.
Well, when are you gonna take mechanical measurements?
I said that.
You're not taking it next year. You're like,
I'm taking next. I'm taking spec. I'm taking shear electronics and current.
oh, you are? But then, what are you gonna do next spring? Both your semesters, next 2 semesters, are probably be out of there. We're supposed to be 17 credits.
Oh, yeah, electronics? I have no idea what I'm doing. I'm just getting my classes done.
Doesn't sound like it.
I'm getting, yeah, it's like, I'm on track. I talked to the advisors. I'm okay.
Both semesters are going to be 17 credits, so if you're not taking, so if you're not
I
doing.
still have to take physics too, lab, and I'm also taking mechatronics. I'm taking.
No, no, but you said it's the fall, it's measurements, and then you take measurements this way. You not pick something out to take measurements this way.
Well, I already taken engineering class. You take another test. I mean, that's a junior class. I'll be like, mechatronics?
Oh.
Dude, I'm not telling you that, I'm just telling you that I am.
I'm actually, I didn't get to take mechatronics in fall. The only sections of another class that I like actually.
Awesome.
You know what, it's 2 to 5, what?
I really don't like higher for you. That's really good. Do calculus.
Yeah, I heard like a lot of work, but like I can't, how hard can we measure it?
Probably pretty much.
Pretty famously estimate.
Well, that's exactly. This is the class about unless there is, I don't know.
That's so neat. It's like taking a physics class that like you have to take air resistance.
I'm taking thermal mechatronics.
Okay, this is a public service announcement. Please check your attendance, at some point. I think I've got it right, but argue with me if it's not, okay? I am susceptible to error, okay? So just check your attendance and let me know if I've made a mistake, all right? Argue it. And if you got lucky and I made a mistake in your favor, I guess you get a free pass.
Wait, why did my roll call get jacked? I literally had my grades pulled up as an 85 and now it's an 80.
Oh, because last week, that's part of the thing, I had marked people present, but I had not marked people absent. And so I just didn't put them in, and so I just marked them absent.
Okay.
Yeah, so that's what I'm saying. You know if I'm mistaken.
I don't remember
What?
We've
How
had
many percent
20
is one
sessions
class?
then, right?
It's
We've had 20 sessions plus an exam, so
And
there's
that's
21.
also attendance to 20.
Yeah,
okay.
yeah, you also get.
Sounds
21.
about right.
Yeah.
I should have 21 points in it.
Yeah, that's about right.
15 days.
Okay, well, have you missed?
Yeah,
I'm
no,
off by
included in my absence days. It says I have 12 present and 3 absent. I mean, I'm a something.
Yeah, I don't know. Well, send me a message.
Well,
Let it refresh, let it refresh.
It's just, I'm official.
I'm off by one day, I think I know, I was like 20 minutes late in class, and I tried to, because I'm 93, which is 19 hours later, I missed one class.
Okay, so send me a message in the Canvas. Send me a
I
message.
just want to show you,
Yes.
right? This is 15 days total, included present and absent days.
That, I do not know why it's doing that. That is weird.
Wait,
I've only missed 3 days.
actually, I'm confused. A 19 out of 21 is a 90, and a 20 out of 21 is a 95, how did that get 3?
Yeah, I don't know if math adds up, but it's
I don't know how that
whatever.
happens.
Okay,
It's
well,
close
again,
enough.
so let me send me out. I think maybe I just take a look at things, all right, carefully.
That's okay.
Just send me a message, and
I'm fine with it.
we'll go through it. Okay.
So I'm getting more than 12 days.
Oh, well, maybe when I was really late, it gave me like half.
No. Whoa. Hold on. No, we've gone through 20 sessions, but we've combined some days.
Oh.
Yeah.
Somebody said 20 days.
Yeah.
Somebody said 20 or 19
Yeah. We combined. a couple of days.
Okay.
All right, we combined some days.
Somebody said 20 days.
Yes.
Wait, Matt, how
I'm
did
not-
Well, okay. if this
Well,
is
I
right-
said sure, that makes sense, but no, it doesn't make
Okay,
sense.
okay.
Yeah,
Okay, so.
it's been less than 20.
Yeah, which I think that.
Do
Yeah. Okay. Okay, we're all set. It makes sense now. Are you calling me a bozo? I'm a bozo? We've missed the 5th class.
Okay. All right. How many classes you go to last semester?
Kindness begins with us. Okay, yeah, you had a question. Sorry, Carlos.
Yeah.
What's up?
For this one?
Yeah.
So I find there's only one stress which is in the head, and there's a shear stress.
Mhm.
When you graph it, Is there only one point on the circle then? Because you don't have the y, or the y is 0.
Okay, yeah. So in this case, right, if you have, we had to figure out what sigma x, sigma y, and tau xy are, right? And once we figure them out, or if it's tau yz, whatever we're looking at, right? Because we're typically only dealing with planes. So there are those 3 parameters. If you have a sigma x and a sigma x and a tau xy, for example, yes, absolutely, you can graph it, right? If sigma y is 0, you can still graph the Moore circle. It's an interesting Moore circle. Okay, let's point this out. I think this is worth pointing out because it's confusing.
Because the line should be straight, right? Between the x and sigma x and sigma y.
So
Like an L.
yeah. All right. So folks, this is fun stuff. All right. So Carlos, you're saying, what if we have a sigma x equal to some value, right? We'll say it's greater than 0. Okay. And we have a tau xy, we'll also say it's greater than 0. And we have a sigma y equal to 0. Alright, does this make sense? Okay, so if that's the case, when we draw the Moore circle, what's going to happen here? Well, we gotta draw it, right? So we go ahead and we draw the first thing is you figure out where the center is, right? The center we can put like right here, for example, right? And this is gonna be the average, right? And what is sigma average? Well, it's just sigma 1 divided by 2, okay? And then the next thing is we say, okay, sigma x is greater than 0 and tau xy is greater than 0. Where is that going to be? We know it's going to be in this quadrant, in the 4th quadrant, if we're thinking about, quadrants. With this being, it's not, but, it's like the 4th quadrant of the green and the black. So that puts us out over here, okay? And I can go ahead and write this as sigma x, comma, whoops, I should do it a little bit more carefully, because that's the average, so I'm going to say, yeah, let's do it like right around here. We agree? That's a point? All right. And normally what we do is we say, okay, let's go ahead and draw the Moore circle. Okay? Just like this. What's important about this Moore circle oops, that's a little bit bad. Let's do a different color. Okay, is that this point over here, that's got to be the sigma y negative tau xy. Okay? When I draw, usually we pick sigma x, all right, when we draw Moore circle, but it needs to line up with the sigma y as well. And on the opposite side, because think about it this way. What is the angle of rotation between sigma x and sigma y in a plane? 90 degrees, right? What is it on Moore circle?
So it's 180.
180. So where does 180 put you? Over here, right? So that's why on Moore's circle, the sigma x and the sigma y are 180 degrees from each other, and they form a diameter through the Moore circle, okay? And remember we did that problem that you so nicely talked about with me when we rotated about the x, right, 90 degrees? It's similar, right? What happened with the tau? Remember the tau flipped from positive to negative. Same thing happens here. Okay, so that's how you handle that. So if sigma y comes out to be 0, there's a good chance that your sigma 2 is going to be less than 0, because it's going to pop out over here. And this is, this comes out of
This is
the sigma average, right, which is dictating here, that's the sigma x plus the sigma y divided by 2. Or it's just sigma 1. Actually, sorry, I should have written sigma x divided by 2. I'm sorry. It's not sigma 1 divided by 2, sigma x divided by 2. Because it's really, this is really, I shortcutted, right? This is sigma x plus sigma y. I mean, it's also, let's just let's leave it at that. Okay. Good. Very, very good. Very good. Good question.
That's the only thing I actually get to do.
Did you just say you're really stressed?
Yeah,
I have an
honestly-
exam for
honestly,
Class 4
it's
in
not
an hour.
Oh, I'm sorry.
No, it's not.
Yeah. Well, I'm sorry you're stressing. I hope this
I mean, you ruined it. Now it's even worse.
It's not, I'm not that original making that joke.
My assignment was a 95, and I've done nothing, but I got one all over since then. That's a 91. I was gonna say attendance. How's it going now?
So
Yes.
we,
Oh, right.
tomorrow we learned something new, but it's not on the exam. And then
That's right.
Today is the last, okay.
Yeah. And this assignment is due tomorrow.
Okay.
Right at the end of tomorrow's class. So if you have more questions on this, or if you have questions about anything through the previous sessions up to today's content, tomorrow's a great time to ask. And then we have the exam on Wednesday. How do you all like having the last session's assignment due at the end of the class versus at the beginning? Does it make any difference to you?
That's better,
It's better? Oh, okay. All right, good. I'll probably keep that then, and for the future.
Me and Italy used to stay up to like 4 a.m. and then we couldn't make it class outside.
Oh, okay. Does it stress you out though when you're in class then, because you gotta finish it by the end?
Not really. Once you got a good night, because after you've done it the night before and you sleep and you wake up, it just makes sense then still.
Oh, okay. Good. Good. All right. Yes, Michael.
Well, I got it too.
Yes.
After session 15, I checked my assignments, it was like 95 or something.
Okay.
And I've done all the assignments since, it keeps going down, I don't know what's going on. That's an unknown.
For the assignments grade?
Yeah.
Oh, well, one thing that happened is I went back. Okay, so I had to grade. You know how you guys have the FBAs that you had to upload the screenshots? I graded those,
Is that
right? And a lot of people didn't do them. And so if you didn't do them, that was like minus 9 points. Because they were either, or minus 6 or something. Like, because they were 2, 2, 2 or something like that.
I was just,
Yes.
this is the same, like, graph that I've been using for all most circles that's worked so far. And for some reason, with these numbers specifically, it's like undefined. I don't. 0.
What do you mean by undefined at 0? But at 0 at the origin?
At y was 0.
So when tau is equal to 0?
Well, like for the principal stresses.
but on note on about the FEA, we will have one more FEA assignment. And, oh yeah, that was the other thing. There was a suggestion that we change the grading policy so that now, if it's many days past due, you will get, if you get it all right, you will get a 25% instead of it just being 0. So there's a slight incentive to go and do those. So good, you guys, we're iterating towards something that I think is, you know.
Is this the only class you teach, or do you teach?
So I taught 2 undergraduate classes, this class and DMC, and then graduate classes I've taught, I guess, 3 different graduate classes. I taught one that I made up kind of based on a textbook on soft sensors and actuators, but we only taught that 1 semester. And then I did robotics and applied dynamics. And if you're a senior and you want to take either of those classes, you can.
What's a DMC?
Design mechanical components.
Oh, yeah.
So that's kind of like why things break 3.
Is that like?
This is
what
why
with
things
CAD?
break 2.
Wait, what was
What's why things break one?
Statics.
Wait, is DMC kind of like? Does it have?
I mean,
some
that's
CAD?
not what they're really
No,
called,
but it's good, that's good.
yeah. What?
Does it have like some CAD? Is it like?
DMC has
design?
no.
Oh,
There's we do.
It's like-
CAD is a prereq for it.
Yeah.
So
Yes, you do.
you can use CAD if you want on it. We do a final project. Usually, it depends on who's teaching the class. But yeah, there's usually not any CAD. That class is a wonderful class. So my impression, you know, this again, I guess this is being recorded, but I think, you know, this class is particularly hard because it's kind of the entry to our department, entry to mechanical engineering, and usually people are sophomores, and so it's kind of like it's a little bit jarring, right? Because I think it's more complicated than statics, right? So that's jarring. By the time with DMC, usually they're juniors and they've gone through some of the other difficult sophomore classes, and so people are a little bit more used to the rigor. I think, I don't know, and I think DMC is a little bit more fun because it's not. We don't derive every. It depends on what you consider to be fun. Some people like to derive every single thing, which, with the exception of the triaxial stress formula today, we've derived almost everything, okay, from you know, Newton's laws essentially, and statics, but applied in a slightly different way. DMC, it's a lot of tables, the way we taught it, it's a lot of tables, and,
It's like thermal.
it's a little bit, I mean, we're not doing steam tables, but yeah, you know, like, they're more tables, and there's more like rules that we bring up, and then you use the tables, I guess like thermo, yeah, to figure out what the result should be in some cases. Alright, in a lot of cases. Because there are things like different factors that you use, and what's really cool is that you cover fatigue. That's like the primary focus of these.
You work with what?
Fatigue. So cyclic loading. So the idea, right? Like we talk in this class about how the stresses, if they're above a certain threshold,
Well, it starts yielding.
it starts yielding, that's failure, right? But with fatigue, you've got vibration and it's cyclic loading, and it turns out it can be much less than the yield strain. But you have that cyclic back and forth loading over time, whether it's a beam on a boat, or a beam on an automobile, or some type of structure, or on a bridge, or some kind of structure on a rocket, right? That vibration induces stresses, and even though they're much less than the yield strain, over time, they can lead to microcracks that form and then cause failure. That's the basic idea of this. So you get these microcracks, they propagate, and eventually the effective cross-sectional area that you have becomes too small, and it fails, right? So if you look at what happens with fatigue cracks, you have like this nice smooth crack where it was like opening and closing, and it's nice and smooth. And then finally, the effective cross-sectional area got too small, and then you get an ultimate failure, right? And you can kind of see where it was a plastic or a yielding, and then a failure, kind of sudden failure. So that's kind of one of the core principles you cover in the tools that you use to figure out if something's going to break after a certain number of cycles. So I like that class. That class is fun. But I haven't taught that class in this format yet. This format is new. Last semester was the first time I taught it with the videos, the website, and all of this.
I like the
Okay, well, thank you. You're in the class. You can tell me otherwise once we're done. No, I really do. If you have good videos that you like from other people, I really would like to put them on the website and just let people have at it. Then
Organic chemistry tutor is awesome, because he doesn't do mechanical engineering, but anytime there's like math that you have to do.
yes. And in fact, we have a video tour of his at the beginning of the class.
You should do
Dimensional
it.
analysis.
My degree pretty much comes from here.
Okay. All right. That's great.
Well, at least I need math class.
Yeah. That's great.
It's good for at least freshman.
No, that's great. I think it's great that there are these resources out there. I think we wanna work together, right? In terms of like, if that's what you're already doing, right?
Well,
why not?
that's because other classes don't have
Well, then just do
videos and like things I can really look back on that are like.
Yeah, the website's awesome.
Yeah, it's like if I'm taking like calc right now, I don't have any homework, and the only resource I have is the textbook.
Okay.
And the textbook isn't bad, but the other thing I've been using is this guy, I don't even know Matt Charlie. He's like,
Oh, yeah.
he pretty much invented DiffEQ for Rutgers, and he has all of his videos. So even though my teacher is not Matt Charlie, we use his textbook, we use all of his exams, his math assignments, all these random things. And he has all these videos on YouTube.
Good.
Because I'm basically taking his classes with our teacher.
Yeah. So no, that's
But if I didn't have that, I'd be, I mean, I don't like textbooks. It's just there. I need someone like.
I think it's absolutely insane that textbooks don't have the answers in the back of the books.
Well, they have like every fourth problem.
It's,
And then there's no work.
That's not even, teachers don't even assign textbook problems from the textbook often anymore. Also, if someone cheats on their homework, who really cares? Homework's like 5% and they're gonna fail the exam, that's on them. And they've just made it impossible to use the textbook to study, because the hell, what good is Bragg's problem, don't know the answer.
Sorry for the
record. Right now.
What?
I'm not gonna remember. You subtract a multiple. Right?
yes.
Problem descriptor. I mean, I got the answer, but I think it's like.
Yes, no.
Okay.
So I'm talking about
So, sigma C is supposed to be right?
multiply this row by this.
Yeah.
Subtract this row.
So when I
Actually, I don't know anything about
this
it.
circle that makes sigma 1 is smaller than
You're
sigma
gonna
1
get
is.
pissed off when you
I know. Did you teach me this first?
Uh-huh.
No. I just.
So the
But the dominant one is gonna be the same one.
You can subtract
I know,
multiple,
you can.
you can subtract
One is positive, one is
right?
I'm gonna try right
yeah, so these are the answers will be like in radius.
Because I need this to be 0.
I would say yes.
That's,
But
I can't do it.
it's, well, I just took like the radius. These little one,
Okay, and that was the right answer.
yeah, I don't know.
Let me take a look. Which one is this? This is
So that's probably like it's,
okay, let me take a look.
or maybe the difference is really small.
Yeah, so there can be a wiggle room, right? Because I put in like 4% usually.
Do you ride motorcycles?
I do not ride motorcycles. I do ride bikes and an e-bike.
You think you like?
How fast? It's a class 2, so it tops out at 20.
Does it have regenerative braking when you're going like stop?
No, absolutely not.
That'd be pretty cool, so then like you would never have to paddle.
That would be pretty cool. On well, no, I mean you have this. I mean, so how do I put it? If it's charged, I can get quite a bit of. It's not that big. I don't think the way I ride, I don't think I would do. I don't know how much more I would get out of regenerative braking because in a car you brake a lot,
Yeah.
at least in a city.
In a car brake though, it's not really using regenerative braking that much. Just cause like you can only stop the car so much with regenerative braking and you have to add the actual. In a bike.
That's because you get damage, viscous damage when you have a DC motor. Yeah. So viscous damping doesn't give you coolant friction, just to stop.
It's pretty. I'm kind of surprised actually, because I thought that with the regenerative braking, it was really just they flip a switch in the motor, and they just tell the motor to go the other way and take power instead of getting power.
It's tricky. You have to change. It's variable resistance, right? So that is if you had zero resistance, that would be like right. So they have variable resistance as you apply the brake. Okay. Let me take a look at.
The difference is small. That's the thing.
But did it mark it wrong if you
No,
did the
it's
other one?
right, it's right. I was like confused because I thought the difference would be higher, but not.
It's very small.
Yeah.
Okay. Yeah, so the problem is not, I probably should have designed it a little bit better so that the difference wouldn't be so small.
Oh, because the answer is 66.7, my was 66.3.
Mm-hmm.
Yeah, because the Sigma 2 is just 0.8 from the outset.
And depending on which numbers you get, it could change it a little bit. Yeah. I'm not 100% sure, but I'm pretty sure I did it right.
Yeah, it's fine. It's like good.
I'm never 100% sure because you never know.
It's like it wouldn't make like a big difference
Yeah.
to use either radius because the circles like
Right. They're very close to each other. That's right. At least for the numbers you got, they are.
Yeah.
Yes.
Shear stress.
That's good.
Also, yeah, for this problem,
Yeah, and then pure. It's 2
we put the formula right for to get like this sigma.
Yes.
Oh my goodness. For the bending moment,
Mm-hmm.
C, we use to find the torque, which is point of moment.
It's a moment, yes. It's a torque, but we call it a moment in this class, yeah.
BZ times Okay, please do.
Yeah, so for the moment,
Regular.
so easy, yeah, it's okay.
But then why for example, is it because it's the lane, same line
Right.
of action or?
Right, it's got, exactly, it's a different line of action, right? Easy, the line of action is this direction,
When you reduce the matrix,
whereas
you
in
just
here, the line of action
That's what
is.
these explain this.
Because for this one, if I want to find the bending, why would I use
PY, no, well, PY, right?
All the circle.
It's oh yeah, so you would use it for, if you wanna know the contribution of bending moment, you use it.
Oh, but it's zero, okay, perfect. Yeah, it's zero, because
Okay, we have
the neutral adds.
Yeah, the radius.
Okay. Yeah, three is possible.
That's right, that's right.
You got it.
Yeah, I keep missing out with like the line of action sometimes.
That's good. Yeah.
My bad, we also find that. I realized that you wrote. Slash makes sense. But just this is called all circles. This is the new 3D stuff, right? This is 2D stuff. Then I have to drop curves and stuff. Then I have to drop
Wait, is there no, is there no transparent?
Nothing shear. Shear. They said I like that because you write a lot.
That's because I got out,
Still 14.
Jones, or the guy that you like, right?
That's even worse.
I don't know.
Oh, no, actually.
Rain hits every rain hits. How many reels? How many reels? Sorry, how many reels coffee is? I say 600. I say 300. It's just 300. 600 is coffee. No, I don't. I thought 3. Because I know rain's good.
That's the best one.
Yeah, rain. Which one is that? The peach one. Oh, like rain in general. I have
I was supposed to.
I don't know, those are also the texture. When they're small. After the race, we day with rain.
I don't mind it, bro. I get through so many emails, it's fucking
Jersey.
I'm right on this one. I absolutely want it. I promise you. I did 27. I had 27.
I can't believe that that's. Who's playing this? Did you see that,
That's what my physics lab was. That's what that's exactly what my like that. Actually 2.5 done.
bro, I have to say, you did that, bro.
6 days that people like, oh, I get to choose this. Yeah, I literally spent 2 plus late.
The school has 700. Yeah, the school has 700 departments.
You guys remember this?
Yeah. In Rutgers or guess what I was gonna do? No, that's just for Rutgers University. There's no way you just have to change. This is lower than the other one because the school actually is much higher. I think. I think like average papers for high school. Look, for Rutgers not whole, it's like 33 grades. Because they just no, they just make it up even it's wrong. Yeah, because it's just a language model, so even if it doesn't really answer, it's gonna pretend like it does because no one answers questions online. Like, oh, sorry, the answer is like, oh, this is the answer. So it's like, oh, this is the answer, and then it makes up the answer. This doesn't look like a real high school. Yo, what the hell? We went to subject to 77%. I thought it was like 90.
how much you want.
Dude, I remember birthday in this one junior year, she would like say something to me, and then you look at her with blank stare, and she'd be like, come on, this is like Spanish one. And she'd be like, I know you know this. And I was like, perfect. No, she was like, stop this, I know you know this. I was like, perfect. I swear to God, I had no idea what you just said. She was like, it was so funny. Well, that's perfect. That's just funny stuff. Actually, I remember one time Rose made jokes about it. She said, oh, like she would like once in a while, like how it's like she had or like she like something like this, like what I can see something that's like and she got hit real big. Like she did a lot of jokes. She said like look at this. 40, so I was like 3 inch and 40. But then one time I did all of that nowhere at 8. I was like, oh fuck. So this is like look. Okay, I'm so confused because once you find it's just still 67 slides.
Is that excitement about this course or something else?
No, this course, this
Okay, well, good, good. Just as a reminder, right, this is recorded, so this is a PG environment. Okay,
Yeah, I think that's right.
just throwing out that it's a
Can that
PG
pick up
environment.
everything in the class?
Huh?
Does it pick up everything in the class?
I don't know, I'm just,
I'll go back and listen to all the times Mike uses profanity. Until they get
You ever seen the video of the professor? He's like, it's like an econ professor, and he gave an example with like the cost of beef, and he said beef 132 times. And someone took a video of the lecture and just cut together all the times he said beef into like a minute and a half long video. It was like beef, beef, beef.
But you have to find it, so you do the information.
oh, and what's up? Come on, let me know, come on, ask a question. I see the
I
frustration.
can figure it out.
You can figure it out, yes, but we're here.
Yeah, I have the right method though. I think it's just calculations. Just gotta do it on different numbers, you know?
Which problem, do you mind me asking?
It's just 2 for 19.
Okay. 19?
Yeah. I'm pretty sure I got it. So.
What's that? I'll be right there. I'll be right there.
So what's up?
It's just question.
Or you have another exam, I see. Yeah, you guys have an exam.
It's a equation sheet.
Yeah. Getting good. Yeah, so with this,
Mhm.
you wanna draw more circles, so if you draw six circles.
I was just thinking, because it's just so to calculate sigma max.
Okay, I'm Mr. Counting.
It's if more circle is at the origin, it would just be the radius, right?
So, yeah, but it's not at the origin.
Yeah, so in that case, it would be, I was thinking maybe you could do, what was I thinking? I was thinking you could do radius, and then you add on top of it
Where the average is?
the
Yeah.
average, it's just the,
Okay, but draw it out so that you can do that. Because I agree, that's a good approach, and that's the approach to use. What I suggest is that you draw it out.
Maybe I'm wrong.
Right, so draw for these, you know, before we were like, okay, use variables, but now more circles.
I know that, I referenced
I
that. I know the reference is.
Yeah, you messed up.
But like draw it
Well,
out.
not in a way that.
Draw it out. Yeah, because I agree, right? Even that example you saw right there, right? The one that you just pulled
Yeah,
up.
I guess the reference to it is valid.
Yeah, C, if you can figure out where C is, right, which is at the average, and you know what the R is, yeah, you can figure out.
Radius plus.
Yeah, so I suggest drawing it out.
Oh, if it's just two equations added, right?
Yes, but so in this case.
I'll draw it out, but I was just, that's why I think it's a calculation error. I just gotta be more careful on my calculator.
Draw it out, draw it out, draw it out.
No, what is he saying?
For section 19, question 5,
Yeah.
we want to get an angle that tells us a transform state.
Okay.
I'm wondering, like, is there a difference between a transform state?
It's just, no, it's just the reorientation of the element. So what's the angle, right? So in this case, it's saying, okay, we wanna get max increment shear stress, so we wanna get, what is theta s? What is theta s?
Oh, so it use this equation.
Well, again, I think the same thing as just saying, draw it out, right? Draw it out, figure out, okay, how much angle we have to have so that we can get vertical, right? Because we're interested in the in-plane
So sigma x, sigma y.
That's right, so this is, well, let's see, what are your sigma x? Your sigma x is 9.4, your sigma y is 46. Okay, yeah, how x y is minus 7. So this is a little bit tricky, right?
That does not count, no. That does not count.
So what we do is we link sigma x and tau x y together, right? And we link sigma y,
Yeah, that's fine.
is that name? No, sigma y and negative
Screw
tau
it,
x
tool.
y together. So if I'm gonna draw
The other stress is.
this out,
Oh, so.
you're right, you're fine, no, you're fine. Except I would put this arrow down here, so this is positive tau going down, right? And so -7, yeah, that's a good place to put it, right? And then
Oh my god, I'm actually,
sigma
I
y
know, dude,
46,
I know
that's
that
a good
too.
place to put it, because then you're gonna have +7 down there. So this more circle looks fine.
Oh.
Now the question is, okay, we wanna go clockwise, and it's gonna be 2 theta, right?
Then one
That's-
PR or
So that we get this vertical,
Oh, okay.
right? So then you would, so, when we gotta plug in numbers, right? So like this middle one's gonna be an average of sigma x and sigma y, right? And, and then the angle, right? So we can figure that out using right triangles. Okay, alright, good. I'm glad you asked. Okay. Michael, you had a question?
Yeah, I mean, for this question, am I just forgetting how to do matrices, or doesn't it just, can't you just subtract this row from this row, but then just leave it that?
So, yeah, so you can go ahead and do this. I highly suggest though that you just.
Oh, when you go out.
Okay.
We solve for the radius for this. But if they're equal, it's gonna be 0.
Oh.
He's cursed more than me last. No, I haven't, I said literally like, I'm whatever, it's not even worth it.
But if we have two different ones.
I got it, I'm crazy, dude.
This is the center point.
Great.
Treating it as she goes.
What's that?
I am Mr.
Say it. If we do what you're saying, it's gonna be the same. Can we say shear stress is the same? You're different.
Do it to yourself.
Okay.
Well, these are.
Oh, yeah, we can't solve it, it's not more to that.
Maybe I should go.
You're right, guys. But one is the same and just stress more. So we use the same coordinate as that, which is that coordinate. And then we got one actually. So it's just the one, so it's 9-0, but there's no difference, it's the same coordinates, that's center point dial is gonna be slightly.
That's what I said. Yeah, that's what I'm saying. How do I find applications? I thought you were Mr.
connect to
But
your.
if it's a high number point,
I'm
doesn't that mean
How do I
you're?
find, so I can find your stress is like max stress or stress.
Wait, is there no, is there no shear here?
Well, let me see, all other stress.
Hey, you know what?
No, Professor,
Chef.
What's up?
what is the shear stress on a circle? A sphere? A hollow sphere.
Oh, did you see the group me? What were we talking about?
No, okay, we were trying to figure this out.
So the group me, right?
Yeah.
There was some
Some conversation.
definite conversation about this, alright?
That's a good point, actually, that's a very good point.
So, but no, so what,
That's just, whatever you get there, George.
let's, I'll go to the board, right, for this, cause this is a good, I like this question a lot. Okay, so there's a question, okay, I think the question is there shear stress in a pressurized, thin-walled, spherical vessel, right? That's the question, right? Okay, so if we draw
Do I do one with T and one with just one T?
like our little funky sphere, right? And we've got an element here on the side,
Just two T.
okay?
No, just one T. Max is two T.
Is that thunder?
Yeah, it was lightning when it was driving down. It was like really bad rain, I drove through it, and then it's nice and sunny on the way here, so it's not happening.
Oh my god, I almost got
Miracle.
tired walk yesterday. Dude, the water was so
Oh,
high.
it's really bad, the tree setting, it's really bad.
It was on 22 where I was, and like literally I was like, cause I was in my mom's Lexus, she has an SUV. Like if I was on my Accord, I would be dead right now.
You would have been sitting in the middle of the engine.
I literally like my engine would have got flooded.
Engine flood, that's it, yeah.
Cause like I was literally driving by so many cars that were just submerged in the water, and I was like thank God, like I didn't know it was gonna flood. I just took my mom's car out because like I just felt like it.
Is that by the intersection where it's like the massive hill by the Watchung Mountains and there's like
Yeah.
a valley bank to it?
So it's like by
I think
Warren, like if you're going up
in
to
the-
Warren on
In the
on
past,
Washington? Huh?
I think in the past that intersection, people have actually died from like flash floods.
Wait, was this yesterday?
Yeah,
Yeah, no,
That's
I was
A
just
bad
driving to
place to
school.
be.
Yeah,
yeah.
it was just like crazy.
Like literally, like I'm driving, it's normal. It just starts pouring rain, right? I'm like, oh, this is kind of crazy. I can't see. I look outside. I just see the water level getting bigger and bigger. I was like, oh.
Oh boy,
It
okay.
was like the rain was hitting the windshield hard. Like
Yeah.
it was like I don't know, like the
the extra
volume
30
coming
minutes
out of the
to get
sky. Just it was actually insane.
It was okay.
Okay, back to spherical pressure vessel. Okay. And you know, I guess it's impossible to not have been reading the news about
Like cylindrical.
a cylindrical, thin-walled
Materials. Yeah.
vessel that had a catastrophic implosion. All right. So that problem is very different than this problem, okay? Because we have internal pressure, right? I mean, in that problem, you could crank up the internal pressure to try to equilibrate what you have with the hydrostatic pressure, but then you are going to hurt people, right? So it needs to be able to have a lower pressure inside than what it has outside, right? And so in that case, you're not only one of the nice things about these problems is that we're not susceptible to buckling, right? And we don't really cover buckling in this class, although if you look in Hibbler's book, and some people get to it, but we won't get to it. But by having a vessel that's in tension and pressure, right? It's all we don't have the possibility of buckling, right? Where like I crunch it like this. So I mean, we'll see what the investigation reveals. But from what they're saying is that they're probably delaminated pieces because from what I read, it was a carbon fiber composite shell.
That and titanium was like two different entire materials.
And so if there's delamination, that can greatly strengthen things, right? But you've got a problem where the larger you make something like that, the more susceptible, and the thinner, right, the more susceptible it is to buckling. All right. Anyway, so that's a completely different problem. But in our problem, okay, we have a spherical pressure vessel, and this spherical pressure vessel is going to have in the wall, right, and that's a really poorly drawn one, but you're going to have a sigma, we call it sigma 2, all right? Different people call it different things, but this is because it's not sigma 1. Sigma 1 is the hoop stress, right? Hoop, there it is, with PR over T. This is out of PR over 2T, right? So sigma 2 is equal to PR over 2T, right? This is a fascinating scenario, right? Because you want to kind of think, if I look at the stress transformation equations, what, if any, shear stress am I going to have? So that would be one way to do it. The other way is to draw the Mohr circles, okay? And so when we draw the Mohr circle, whoops. Oh. We draw the Mohr circle out. What's the first thing that we do? We look at the average, remember, for sigma x and sigma y. Okay, so what's the average here? Well, it's just sigma 2, right? So sigma average is equal to sigma 2. So we can put it out here. We'll say it's right here. Okay. When I plot my sigma x, when I plot my point, right? Like if I had a sigma x, right? I would do like a sigma x, tau x, y, and I would do like a sigma y, negative tau x, y. All right. But sigma x is equal to sigma 2. Sigma y is equal to sigma 2. Tau x, y is equal to 0. Sigma 2 is sigma average. So everything I plot right here is just on this point. So the whole Mohr circle is there. That's it. It's just the point. Now, if I'm at a point and I rotate, I'm still at the point. And is there any shear stress? No. So what happens here, right? I can draw this element. Really bad handwriting. All with sigma 2s. I can draw this element. All with sigma 2s. It doesn't matter. Any rotation I do about a normal to that surface is going to be exactly the same. Exactly same state of stress. So the shear stress for any rotation is going to be 0. Okay. And it just is a point on the Mohr circle. And if you look at exam 2 from the spring, there was a problem that had the same kind of result. Okay.
Why is sigma average just equal to sigma 2? Is it just because
it's because well no look, so look, sigma 2 and sigma 2 are the same, right? So sigma average is just sigma 2 plus sigma 2 divided by 2.
Yeah, okay.
So it's just sigma 2. Good. Good. I'm glad you asked that question. Does that help a little bit?
Yeah, that's
Okay.
I don't think like a dot or like trying to see how would.
It's a dot.
So what's your opinion on the summary then? What do you think?
We're on YouTube. I can't say anything.
What's
my opinion? Like on what?
What's the elastis module of carbon fiber?
Okay,
Does that have
so
an effect?
And now you're like,
yes, it can have an effect.
Screwed into the.
The yield strength is really what they're most concerned about, right? But yes, the elastic modulus can have an effect as well.
Yeah.
So for carbon fiber, the yield strength can be quite high.
You can't do that, no, you
And
I mean, that makes sense. It's for
The-
like,
yeah,
they
so
put
like,
race cars and
also very late.
planes.
right, now you guys are like, what? And it's usually, it's carbon fiber with an epoxy, usually, all right? I mean, and we do some stuff with this, but the reason that it's so wonderful for aerospace and
It's light.
it's light. It's its strength to mass ratio is amazing, right? And so you could have carbon fiber. You can have glass fiber as well. They're fiber reinforced. Doesn't that have the strength on there? Yeah. So stiffness. I mean, it does end up having a very high elastic modulus for its mass as well. Right. So the tensile strength. 3 gigapascals. All right. That's
It's like,
right. We usually think in terms of hundreds of megapascals.
it's like what, 20 times less than steel.
Well, it says 10 times more than mild steel, right? Remember, with the steels, you can change the yield strength without affecting the elastic modulus
Yeah, you said,
with
like,
heat treatment and composition.
Like combination of steel and other things. It's typically the same elastic modulus.
Right. It's typically 200 gigapascals, 210
Okay.
gigapascals. Okay, for elastic modulus, but the strength can go all over the place. We're gonna get wet. I'm gonna get wet walking back to the office.
The flip memory was looking at my code this morning, being like,
It's not gonna
I
stop.
love it like car, so, yeah.
It's not gonna stop.
Not for a bit.
Although it says it's gonna be light, doesn't look
I have
like
a-
light.
It's
I have a
supposed to get better,
raincoat.
like, in 10 minutes or so.
But it's in the office.
Supposed to get better.
if you wanna ride to the office.
No, it's okay. I'm just right over here. I'm not gonna get that wet. Okay, thank you, though. That's very kind of you, George. Are we about to be like the people? Are there people out there getting soaked?
Yeah.
Yeah, we're about to be those people too, aren't we?
You know,
Is there an engineer rain dance you can do?
An engineering rain dance. Like to make
Well, not word, but like, oh, reversing back.
reverse.
Reverse.
I don't know. Well, I mean, right? We had with all the smoke, right? They were saying that was actually keeping things dry. All that ash that got into the air. So there you go. There's a toxic way to do it, I guess, or a
Bigger bonfire.
yeah.
do you know how to do this? Find the angle of rotation. What is these organs? So, I don't even know, like,
This problem,
Different angle of which.
the PY.
It's like an arsenal.
Yeah. And then the PC is the force going that way. So, yeah.
So 0.4, or it goes down that side thing. That one or does that look up one?
Yeah, break it down.
I think that one is the answer. Which angle is it?
oh, here it is.
No,
Yeah,
that's
so it's
tau over like 1 minus 2.
What is it? It's a
Absolute
So
Sigma x minus sigma y. Sigma x minus sigma y.
Yeah.
Sigma x over Oh, it's just average.
Yeah, it's, tau or the average.
Okay.
So it's not the average, it's, the average would be plus.
Oh.
No, that was positive. At least on that. I think the color is. Care about the cells must be better. I left on my car because like, there should be a little bit of like rain around here, but these are gone.
I was going 30 on the highway because the traffic was like
Yeah, I remember, yes. I remember it too.
an hour and a half to get.
I think worse than taking differential equation examples.
So the easiest
Oh, yeah.
Do you see this one? Water.
is maximum
I don't know about that. We'll wait to find out again.
Well, I got it. It's so funny. It's so humid that like it'll be the sunniest today nowhere. So it's downpouring. It's where
Oh.
Yeah.
like UT storms.
Yeah.
But not getting this
Yeah, you'll be well.
it's my backwards. So if I move this,
I gotta
move
you guys get the rest of
X, all is over here, all is doing is the expansion. So, see, this is the X is actually two. Talking. And it's also.
I don't know. I'll be okay. So
It's probably not. I just have hella examples. What do you have equation wise for the vibrations and the force? Because like, I was looking at the textbook and I just can't make any sense of it. Like, I don't think we're supposed to understand it. I don't even know what like the important.
This is kind of, this is my fancy example.
But I would say.
Oh, we got like everything, yeah, I showed them what you have to do for, so you want to do, yeah, PR over yeah,
I just have first example.
but you don't have to repeat it, but yeah, you see that. And then do you know exact equations?
I mean enough. Just check if it's equal and check if it's contiguous.
I should write it right
I'm actually understanding like. I mean, I'm gonna follow the process. Like, it's just set.
Yeah,
exactly. What's FX? Yeah, you just plan with integrals to
Yeah.
I mean, I don't think it would be that bad. I'm gonna be honest, I did not.
Throw some of the home science shits in there. It's just like, it's just gonna get really gross, I feel.
If you just get stuck, that's a problem. I'll be honest, I barely understood this before like the weekend.
No, yeah.
I just learned it all.
Yeah, and it's really not that
Like
bad.
the way he explains shit is so complicated.
But like,
just
did you watch some of the trainers videos?
no.
Start to read.
I followed
Matt Charlie, he's so
I'll tell you what I followed.
he literally taught all of my friends the semester and literally the textbook is his. The math assignments are his.
I've been following this guy. He actually has really good examples. You just follow examples. What's this guy?
Shear.
Transfer shear, betting about
Like just click on it. And this is all of his instruments.
He
has one for
This
each.
guy normally just teaches it, but I guess we don't.
Yeah, because he doesn't know what you're saying. So literally the entire course was made by him, so watch it. He explains it really well. All his videos are like 6 minutes long. Because what they used to do is you'd watch an intro video before the lecture, and then you just understand everything, and then you just like go more in depth. But every video gives you an overview of all the topics. It's actually crazy. That's good to know. And just trust me, like honestly, just like before lectures, like watch the video that corresponds to like. We'll be okay. I'm not walking out.
that is going to be that force action that way. You see the shear, internal shear bar, and that transfers shear stresses to the max because I say transverse shear
And then
stress,
where
yes,
is
you
zero?
also have twisting.
Zero?
Twisting is gonna improve PY as well.
So then what's this, cause I thought this was
So,
T.
Oh, I missed it.
So
I missed it by
this
3
one,
minutes.
remember, is,
I'm not sure.
yeah,
I was trying to follow.
this
Wait, no, it's not.
is-
That's
that's
a-
a-
this
this
is
is
538.
horizontal shear stress.
This
So
is
this
25.
said these one
Oh,
this one taught me is
Oh,
that's
that's
shear stress.
You understand that?
Both of them
Took me about 3 minutes to do that.
So this is causing the bend.
Well, that's when it's twisted. That's just homogeneous. Yeah, and if it's anything else, it needs to be.
PY is causing a force. Twist, it's inducing this
Yes, yeah,
shear
this
stress
is an
downward.
It doesn't exactly.
That's just like the.
I'm just gonna-
I just don't know about the transfer shear stress. Remove this stuff.
Yeah, I'm
Transfer
sure.
stress
But I'm just gonna
produces
pretend it's
shear
a
force
differential
upward.
equation to show
And
why.
then you over IT, or you can just say, hey, it's 4/3 times tau because he knows that the math. That's the. Yeah, this is why we're here then.
Oh, that's just force times A.
That's right.
Or force over A.
Yeah.
Force over A.
Yep.
And then, so you do that for all of the different forces, and then you can just use the sigma value line for force over.
That's right. You got it. Okay. Cool.
You're drawing out more circle, it's just,
Yes.
is that on the right or left side of the circle of the decay?
Okay, so when you draw. When you're doing more circle, okay, what you want to make sure that you have happen is you draw these combinations. Sigma x tau xy and sigma y minus tau xy.
Yeah, so, okay.
Right, so it depends, right? But
Yeah, right.
typically, not always, if both of these are positive, right, that means that this, the way we use our nomenclature, that this is gonna
Or,
be
no, there's two
below.
sections with the same lecture.
Yeah.
Okay, and then
Yeah.
this one, wherever sigma y is, right, so this is, right, so let's say, I mean, it could be over here, for example, or it could be over here, I don't know which one it's gonna be, but it's gonna be opposite. Right,
Gotcha.
okay,
Alright, that makes sense.
okay, like that, right, it could be one of those. Okay, good, thank you for asking, Tyler.
Well, I didn't drive.
All right.
Well, I did drive it out.
Keep it real, we'll have tomorrow kind of as more information on plane, it'll be a new topic, plane strain, not on the exam. And if you have questions on this assignment, or, I mean, we go back all the way to, beams, really. We ended right before exam 1 on torsion. So beams on, so there's a lot of material for exam 2. All right, have a good one.
Thank you.
Thank you all.